There. Okay, good. Okie dokie, artichoke. Here we go. So, can't remember if I told you guys, but I'm dealing with some carpal tunnel and my handwriting is really terrible. And so what I decided to do was I posted these notes, which are, yes, they are the textbook. I know, sorry to disappoint. I will be following the textbook. I know, crazy, right? I stole all the source code of the textbook and then I added little boxes around the stuff that I would have written notes about. Okay, and so so I went through and I did that. No, that's didn't change a thing. I'm not claiming to own it at all. And it's open source. So which is how I got the source code in the first place. But yeah, so I don't know. Is that plagiarizing?
Not really.
Not really. It's open source, right? Open for business. Anyways, so what we're gonna do is we're just gonna work through these boxes. At first, I'll just get rid of the stuff that I don't want to talk about. But then I thought, well, that's kind of rude if you wanted to have maybe some extra talk around it. So it is just the chapter as you read it. Maybe. Either way. But I'm just highlighting the things that I would have written notes about. Okay. As promised, oh, you know what? I'm going to open this in Notability instead so I can have this pointer because of all the people online. So what I was talking about are these guys. Okay. Hopefully that was obvious. My goal is to do the theory today, introduce all the definitions, notation, all that kind of fun stuff, boring stuff. And then I've got the exercises that I want to work through highlighted in each of the sections. Let me just scroll down there. So here in any of the exercise portions, these are the questions. Yes, a lot of them from the first section. That's fair. There was one in here, but it wasn't in the source code, so they must have taken it out. Anyways, whatever. Those we're going to work through on Friday. Okay. And so if you work through them beforehand, there's a lot of solutions in the back. If you're feeling confident, feeling good, then you don't need to come on Friday, right? And so because we've got this weird schedule, I'm just trying to make it easier for everyone. I'll still be here. Everyone but me, I guess. Same thing, 1.2. I also snuck in between 1.2 and 1.3. We were supposed to do 4.2, but there's not really anything that we're doing in there. And this was, I was trying something and then I forgot to take it out. You can just ignore the double there. It's trying to get fancy, but then it screwed up the numbering and whatever. But I inserted it there. It's really just these laws that I'll kind of maybe briefly talk about. And then we don't really do anything with those until later. So come back to it later probably. But that's what I want to kind of have the setup be. Boring Mondays, fun Fridays, right? Or exercises on Friday. Okay. I've never done this before this way. So we'll see how it goes. I don't know. Any questions before we start?
What point in the chapter? This is just 1.1.
Yeah. Yeah, these section numbers will match exactly. and the exercises and everything. I just put boxes around text. All right. Chapter 1 is on set theory, set notation, and just kind of sets. And so intuitively, right, a set of anything is just a collection of objects or elements. Okay. In math, we call them elements. So elements of a set. Okay. So when we're talking about sets, one of the most kind of difficult things that we have to talk about is, okay, well, how do I describe this set? There are some obvious sets, like the set of even numbers, set of odd numbers, right? Set of integers, right? That kind of thing. And so there are some obvious sets, but sometimes you want to get a little bit crazier. And so what we do is we usually use capital letters, often from the beginning of the alphabet. I was reading this super old textbook. I wasn't reading it, I was skimming it. You got me. But I guess the beginning of the alphabet is traditionally used, and at some point we kind of lost this, but it's still sort of true. But the beginning of the alphabet is traditionally used for known values. So the set A is the numbers 1, 2, 3, right? And then the later part of the alphabet is for unknowns, right? X, we don't know. Y, we don't know. Z, we don't know. Anyways, just kind of a fun tidbit. But if X, so X, any element is a lowercase letter, okay? And so an element of A, so a generic X, is just a placeholder for some element that is in A. And so the notation that we have here, right? X is in the set A. We read as X is in the set A. Often I'll just get lazy and say X in A. Right. If X is not in A, you just draw a line through it. Not in A. No. Like I was saying, there are some kind of easily defined sets, right? For example, binary digits. We can say B, the set of binary digits, is the set of 0, 1. Whoops, my curly brackets. So sets, especially if you know the values and you're listing them, any sort of set is contained in curly brackets. Maybe I'll say wrap sets in curly brackets. Oops. And when possible, right, we use a letter that is kind of helping us remember what the set is, right? Or decimal digits, right here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, curly brackets separated by commas. These are the basic components of sets. Now, if you've made a list and it's obvious what the continuation is, whether it ends or it just keeps going, right? Then it doesn't really matter, but you could have something like this or something like this. The ellipses, so the 3 dots, the dot, 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 ellipses. You can only use those when it's obvious what the continuation is, right? So, any questions so far? No. I feel like I can make this bigger. Okay. We're gonna have these reserved sets that we will assume that you know what I mean when I say the set of natural numbers, the set of integers, right? That might need a refresher, maybe. Okay, the set of positive numbers. So we use this kind of fancy kind of, oh, that's the set of real numbers. Use a double back, and then that's how we make these fancy numbers, right? P, N, Z. That's how I would write them. You don't have to get too crazy. We just do a double back, and then you know that it's the set of positive integers. That means you have to remember what an integer is, right? Integers are any whole numbers, right? Including 0. Natural numbers are all the positive numbers, including 0. I think there was debate there, but that's why we have the P, which is the set of positive numbers, which excludes 0. Otherwise, P and N are basically the same. Q is rational numbers. Okay, that one's hard to remember, I find, right? Rational numbers are what? They're fractions, right? 21 over 72. I don't know. Maybe that reduces. Who knows, right? But these are fractions. Yeah.
Small question. So like, is P gonna be the same as N? You know how it's like it's positive numbers?
So yeah, the only difference is that N has 0.
Oh, okay, and P doesn't.
Yeah,
Oh,
it's like a minor. I feel like it might be just a little bit of a hang up on the author's part. I'm gonna go with the natural number. We're mostly gonna be working with integers, natural numbers.
Yeah.
But yeah, so subtle. Let's see here. No 0. No. Anyways, real numbers. Real numbers are any number that you can think of from negative infinity to positive infinity, right? And so here, this is from negative infinity to positive infinity. And then we have complex numbers, which we're not going to worry too much about. Okay. They make kind of a cute note about just remembering that all this notation is meant to help you, right? It's meant to save you time. It's meant to kind of be more concise, right? And so although it's a lot in the beginning, especially, you know, coming off of summer and stuff, right? But it's meant to help you. And so if you kind of approach it from that perspective, it makes it a little bit better, I think. Set builder notation is just a way of communicating sets where it has multiple components. And so Q, the set of rational numbers, is the set A over B. And then this little guy here, let's see. You can read it as such that, okay. So it's the fraction, the general fraction A over B, such that A and B are in the set of integers. And of course, B can't be 0 because you can't divide by 0, right? And so it's just a way kind of to almost articulate what the set is without just saying what it is, right? And so you don't have to say it can be 1 over 2, it can be 1 over 3, it can be 1 over 4, or it can be 2 over 2, or it can be 2 over 3, it can be 2 over 4, right? That would be crazy. And so here we just generalize it And the best way to communicate that is with set builder notation. Okay? And here it just talks about how to read it. Okay, so A over B, right, is just any fraction, A over B. And then here, this vertical line is read that such that or where, if you prefer. And you can use a colon if you want, right? So it can be a vertical line or a colon. Yeah. I was gonna say something, but I'll save it. What was it? I know, rude. Fine. Can I write an integer as a rational number? Right. Let's remind ourselves what the integers are. Whole numbers, right? -3, for example, I could just rewrite as -3/1, right? And so all integers are rational numbers, but not all rational numbers are integers, right? Only some of them. Right? An infinite number, which is confusing, but there's a larger infinite number of rational numbers, and an even larger infinite number of real numbers. Okay? So, all right, kind of mind-boggling. Don't think about it too much, or maybe do. So we'll use set builder notation. You'll be kind of fluent in reading set builder notation, and it's not too bad. Is that me? It's like a ring. I don't think so.
I have a question. I have a question.
Oh, yep. Maybe
Yeah.
that's what it was.
Why you didn't include the irrational numbers?
They're in the real numbers.
But sets are included in the real numbers, right?
Yeah, so irrational numbers are included in the real numbers along with all the other ones. They're just all smacked together on the real line.
Okay. Thank you.
Nice. Okay. This is like the one definition that I didn't highlight because I thought it was getting excessive already. But of course, a finite set is just a set with a finite number of elements. That doesn't mean that you have to be able to count them, right? It's just you could if you wanted to. Okay. Obviously, if it's not finite, it's infinite, infinite. Why don't we call it infinite? Gotta wonder. That's how I remembered how to spell it. Infinitely or definitely. Nice. All right. So any set is going to have some number of elements. It's allowed to have no elements, making the empty set, spoiler alert. But the number of elements in a set is called its cardinality. Okay? How we denote the cardinality is kind of somewhat confusingly the absolute value bars. So 2 vertical bars around a set means that it's referring to the cardinality as opposed to a number, right, which is the absolute value, right? Context is our only clue there, but is the cardinality of the set A. Oops. There will be questions where we have to find the cardinality, right? And so it's good to have that one in our back pocket when you see those vertical bars, right? Especially in a set situation, then you're talking about the cardinality. Right? All right. What more about sets? Well, we can have subsets, just like we talked about, right? Integers are a subset of the real numbers, and I skipped a few, right? But that kind of thing. And so if we have two sets, A and B, generic sets, okay, then we say that A is a subset of B if and only if, which I usually abbreviate or use IFF, if and only if I'm writing it, if and only if I'm writing it by hand. So if and only if every element of A is an element of B, right? We all know what a subset is, I think, right? If you have a set that looks like this, and we will be using this kind of visualizing technique of the circles. They used to be called Euler circles. Now they're Venn diagrams, kind of thing. But so you have a set B, and then if A, all of A is contained inside of B, then it is a subset of B. Okay? And how we denote that is that A is contained in the set. So I say the contained because the C reminds me that that's what it is, right? Contained in the set of B. Just means that A is a subset of B. To use these sets that they've made for us so generously, what's the cardinality of A? Nice. I'm going to write that. The cardinality of A is 3, right? 3 elements in A. These are crazy. Cardinality of B, 1, 2, 3, 4, 5. Could B be a subset of A just knowing the cardinality? No. Right. It's 5 elements. 3. No, can't happen. Right. So already we know some kind of basic things, right? Laws. Okay. Here's what we were saying before, right? The set of natural numbers, right, which are the positive numbers including 0, right? Positive whole numbers including 0. They're a subset of the integers, which are all the whole numbers from negative infinity to positive infinity. So far, makes sense, right? Then all those numbers are a subset of the rational numbers. All right, all the fractions, I can rewrite all the integers as fractions by just putting them over 1. Then those are a subset of the real numbers, right? All the numbers we can think of. And the real numbers are a subset of the complex numbers because they have that whole I squared where I squared is -1. Leave it. Extension. Order doesn't matter, which I guess I should have said earlier. But the set of 3, 5, 8 and 5, 3, 8, they're the same, right? And so S is contained in T and T is contained in S, and they're all happy together. Yeah. Brings us to set equality. 2 sets are equal to each other, okay? And we can use the equal sign, but we don't use it lightly, right? As we'll find later. But A and B are equal to each other if and only if every element of A is an element of B, and conversely, every element of B is an element of A, which is to say A is a subset of B and B is a subset of A, and therefore they are equal. Yeah. Any questions so far? All right. Here they even talk about the if and only if, very particular. But what I want to talk about is the empty set. Okay. Sometimes there are sets with no elements, and so that's when we have an empty set, and we denote the empty set by a 0 with a line through it. So if you're in the habit of writing your zeros with a line through it, you better stop that right now, because it means something completely different. It makes sense for like Wi-Fi passwords and stuff, right? Those O's and zeros, why? But otherwise, no, it means the empty set, and that's completely different from 0, right? 0 is an element, and thus not an empty set. Okay. Little snarky from the authors. It is clear, we hope, from the definition of a subset, and I hope so too, I guess, that given any set A, we have A is contained in A, right? I can create a subset out of A that is just A itself. I can do that. I don't really feel like doing that, but I could. And also the empty set is always contained in A, right? It's an option. Okay. If A is non-empty, then A is called an improper subset of A. Okay, bless you. Which means that if the only subset that you're making out of A is A itself, that's improper. It's not a real subset, or shouldn't use the word real anymore either, right? It's not a proper subset, it's an improper subset, right? But any other subset of A, right, that's smaller than A, including the empty set, are called proper subsets. Okay. This one got me. The empty set is an improper subset of itself. But it makes sense. If you think about improper subsets, or when you take the entire set as a subset, but the empty set has nowhere to go. But it's kind of fun. It's not terrible. It's not important. Oh yeah. They have all these debates going on. Please note, not everyone's in agreement, but I think those are really fun to read. I don't know about you guys, but
People that are like, people with like their masters and doctorates in math are literally arguing about a set that has nothing in it.
Yeah, I think there was even a note about just continuous argument about the definition of a set. I think in the very beginning, I'm not going to scroll there because it's going to be too far away, but yeah, in the beginning, they have a note about some sort of feud, very juicy stuff. But yes, that's exactly what they're doing. Maybe it's their only joy. These are the exercises from this section that I'm parking lotting for Friday, but you obviously have all the knowledge or all the theory, I'll say, to kind of work through these. Okay. You have to list 4 elements of each of the following sets, which means that you have to read the set builder notation, right? And a lot of these have answers in the back of the textbook, right? The answers that are missing, I'll post them. I need a little bit of a breather. So how about by Wednesday sometime, I'll post them and then you can check your answers and see if you need to come on Friday or not, right? Maybe you're all gravy. Maybe you've done sets before. I find unless it's a very upper level course, we rarely go deeper than this into sets, but we cover sets in a lot of different courses. So probably seen sets before.
I thought like. when I
It's a whole field.
Oh, yeah.
I know, not my field, but somebody's field. But yeah, people are working with sets. All right. Set operations. We can do things with sets. And this is kind of where we venture into my realm of statistics. We use sets and set operations a lot in statistics, especially in probability. And so if you've done any statistics course, then you'll be familiar with this. Okay, but if we have two sets, right, we use A and B to just denote two generic sets. Okay, the intersection of A and B, which is denoted by an upside down U, okay, is the set of all elements that are in both A and B. Okay, so how I'm going to read this intersection is and. Okay. And so here, A and B. I should be saying A intersected with B or the intersection of A and B, but I probably won't. Too lazy. So A and B, and that prompts me too, right? When I say, okay, A and B, and this is where we're going to start thinking about Venn diagrams. Oops, that's a B. It's a real B. Right. A and B would be that overlapping region, right? The elements that are in both of those sets. Now, we use these Venn diagrams just to visualize things. There are a lot of times where there actually are no elements in this overlap. Okay. Yay. What a segue to disjoint sets, but it was unintentional. But we still draw them as overlapping, and then we make a note that it's the empty set. Okay, if there are no shared elements, that's possible, but we use this drawing just generically. Okay. And okay, so that's and disjoint sets if they have no elements in common. Okay, so visually it would look like this, right? There's no elements in common. And let's see here. Oh, I'm on autopilot. Sorry. There.
If there's two sets and they don't have any like common elements.
Yeah.
Would that like upside down U thing just represent the empty set?
Correct. Ding. Nice. Yeah. So if I tell you that the intersection of A and B is the empty set, then you know that they are disjoint, right? As opposed to the union, okay. I like to introduce the union first, I guess. I'm realizing now, because the union is denoted by a proper U, right? It's not a U, but it's the union. And so then I use that to remember that the upside down one is not the union, therefore the intersection, right? And so let's see here. If you have the union of A and B, I like to read it as A or B, okay, meaning any element, as long as it's in one of those or both, okay, that's an important distinction. So if you have A and B, then A or B does not care, just floats around If it's in one of those or both, it's satisfied. The union is going to be a much bigger set, right, than the intersection. So if A is the set 2, 5, 8, and B is the set 7, 5, 22, why? I don't know. Then the union of A and B is going to be all of them smushed together. If there are duplicates, you only write them out once. Okay.
Wait, is the union just like any element, or if there's an element either A and or B? Then
Yeah.
that's what the union?
Correct. You just smush them together. Here, I'll say, if there are duplicates, only write the element once. A lot of the time there's some universe where we're drawing values from. It's super nice when that universe is really, really small, like the set of natural numbers less than 10. Right? What would that be? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Not 10. I'm done. Right? Then those are the only values that I care about in this universe. Right? And so that would be the universal set. Okay. We use the capital U for the universal set, so you don't want to be using that for anything else. Okay, and that's kind of across the board. It's reserved for the universal set. Okay. And was there anything fun in here? No. Anyways. The only reason I mentioned the universal set is because some of the questions will say, consider the universal set these values, right? And then you're restricted to only those values, making the questions a lot easier to answer too, right?
Wait, is universal set also representing like not real numbers, whatever?
It can, but it's usually up to us to define it for that particular problem. So it's more one of those things where I would say the universal set is this. What is, you know, a subset or something like that. But it's good to remember. Hey, we've already seen these. I couldn't help myself. Had to draw them out. But I think this is where I stole that note about Euler. But then they wrote some note about a constellation. If it's any constellation, Euler has a ton of things named after him. So they figured Venn could have this. Have the Venn diagram. But even Venn, when he was developing the idea of the Venn diagram, he was calling them Euler circles. That's where I got that from. Kind of fun. So we can visually just kind of understand what the intersection, the union are. Okay. In terms of 3 sets, it might be handy to know, oops, it's a terrible circle. I should let it finish my circles for me. Nah, whatever. If I have A, B, and C, that's how I would draw my Venn diagram. I've seen some crazy Venn diagrams. Have you guys played Keep Talking and Nobody Explodes? You guys played that game?
I think I've heard of it.
Yeah, it's like this intricate game of logic. And anyways, in one of the, so there's all these different instructions and you're supposed to follow the logic and then figure out which wires to cut.
Oh, that game, it's like flip the phone.
Yeah,
Oh,
yeah.
like two hands.
And so, but one of the logic games is this huge Venn diagram. It's like, I'll see if I can dig it up. And a fun game, actually. It was very stressful for me, but it's fun. If you're into logic, that's your game. All right. The complement of a set is essentially just everything that's not in the set. Okay. So if A and B are sets, then the complement of A relative to B would be B minus A. So we are allowed to subtract, add and subtract sets if we want to, but mostly subtract. And so those are the elements that are in B and not in A. Okay. Usually what we're talking about is the universal set in this case, okay, for the complement. Okay, so if we have some universal set U, then U minus A, so you just have your universal set, which is often denoted by a rectangle around your Venn diagram, right? And so here I have my set A. It's a subset of the universal set, right? And the complement of A is going to be everything that is not in A. Okay. And how we denote it is, and this varies from textbook to textbook, A superscript capital C, the complement of A. The complement of A. So it's just all the elements that are not in A. Oh yeah, sometimes I get lazy. But if you've done any calculus, you know that's bad, right? I use a little prime. But that's because I was doing stats and we left derivatives far behind. We were allowed. And context, right? Context will tell you it's on a set, just like the absolute value symbol. Okay, so if you kind of move beyond the universal set, referring to the complement of A, you can take B minus A, which is just all of B, but then you take away A. Pretty intuitive stuff, I think. I hope. Okay, and there are some more examples here. Feel free. You can even have either take away a complete subset if you want. Why not? Okay. And that's when we talk about the symmetric difference. I don't know, but for some reason I have a hard time with this one. I don't remember it. Just isn't sticking. And that's okay. That's allowed. As long as you remember what it is that isn't sticking. So if A and B are sets, obviously, the symmetric difference of A and B, which we denote by this circle with a plus inside, that's kind of confusing, I guess, is the symmetric difference of A and B. What does that mean? It's the set of all elements that are in A and B, but not in both. Okay? So it's taking away that overlap. Yeah. Looks like this. Okay? I think part of my problem with why I stumble upon or stumble over this one, is I rely a lot on etymology, so kind of words guiding me and helping me figure out what I'm supposed to be doing. But the symmetric difference, it doesn't speak to me, it doesn't mean anything to me, right? So if you come up with a way to remember, I mean, I'll just remember it, it's fine. But all I'm saying is if you're having a hard time, then I get it. I do too. But this makes sense though. The union of A and B minus the intersection, that I can get behind. Questions so far? Here's a question for you. You guys used Sage Math? Sage cells, does it mean anything to you? I'm not expecting you to have, but you are in this kind of computer-y program. Who knows what you guys are doing? I only ask because, well, I haven't used it. I've used Sage cells, but for other languages. And so what I could do is I could try to incorporate these into your assignments if that's something that you'd like. It means I would have to learn this kind of weird looking language, but they're all the same once you kind of learn one or two, it's fine.
That just looks like an array.
Yeah, so this I'm totally fine with. I would have loved to see round brackets, but whatever, I can get over it. It's this that why do they have to be, so when we're querying it, why does it have to be in square brackets? Maybe it doesn't have to be. Maybe they're just being weird.
Not to use square brackets for arrays, which are not sets. Java makes you do that because the brackets represent different things.
See, you guys, yeah, you guys know this stuff. And it might be fun to play around with, right? Yet. I certainly don't know it. It took me a while to figure out what this S range, not too long, but I was like, S range 5 to 50. Okay, so some sort of range 5 to 50 going up by fives. I nailed it, but they don't do them in the right order. But 5, 10, 15, 20, 25, 30, 35, 40, 45.
I think I know what that like range part is doing. It's probably calling a different piece of the program to go and run some like equations or something like get with a formula. That's probably what
yeah. I just didn't want to look it up, but I feel like I figured it out. All right, what does this thing do? Right, and I like playing around with stuff like that, and maybe you do too. Who knows? I'll try to make some questions in your assignments, but no guarantees because it might not work. Should be able to. Anyways, I was curious if you'd used it before or no. And you guys don't see arrays until later? Is that what I was hearing?
Halfway through. Yeah, middle.
So I've got some time then. I think it would be wrong if I was the one to introduce arrays.
It would Sarah would be mad, but or she might, be happy that she's not a teacher, but
I'll just let her know. Don't worry, Sarah, I got this. Just like
Just let me know.
Cool. No, she might be into it. Take a week off.
Maybe this can. That's it.
Yeah. Yeah, right. I feel like Ken would
Ken would-
probably
Ken would
ask
probably-
me to do it. It's like,
Ken
can
would
you
probably
just
leave
can you
and
just
then
do
just start
it? Can you just do it? Um those guys.
You bring up the idea that Ken would be out the door.
Oh, what a guy. All right. Here's our brief point about laws of set theory. What I suspect happened here is we have to talk about some stuff. And so now it's in the notes, but we're not actually going to use it. So we'll just kind of talk about these laws. Okay. And on the one side is going to be one, and of course the box drew over it. Hopefully you can still get the gist. This is 1 prime, 2 prime, 3 prime, that kind of thing. It's just another version. So if on the left-hand side you have the union, so A, the union of A and B, well, that's the same as the union of B and A because order doesn't matter, right? And same thing with the intersection, right? A and B, B and A, same thing. Associative laws, right? Distributive laws, identity laws, complement laws, idempotent laws. The union of A and A is A. Well, no duh. A and A is A also. Yeah, got it. The only one that I'm somewhat concerned about, you see, oh, is not that one, is De Morgan's laws. But we're going to see this later. I'm fairly confident in logic. And so, but De Morgan's laws is not quite intuitive, I think. So if you take the complement of the union of A and B, then if you kind of break out those brackets, it switches it. So it switches it to an intersection. And there are proofs and things that we can do, but just take my word for it. How about, all right, you can visualize it. Right? How do you visualize it? Did I bite off more than I can chew here? Maybe.
Figure out how that works, like the complement.
So A, yeah, okay. Here's the union. Here's A, here's B. Yeah, so where do we start? I say I'm not going to do the proof, and then we're going to do a visual proof. Okay. A or B, let's start inside the brackets, is going to be anything in A or B. But I want the complement of that, which is going to be everything outside, but in the universe, of course. Now, is that equal to not A and not B? So it has to be not A. Now, it might be helpful to do, oh boy, how about this? Gonna corollaries. Is that equal to, and I'll do this. A, B, and I wanted not A, which is everything not in A, but also and everything that's not in B. Same idea. If I'd been more careful, it would have been more obvious. But if you put these on top of each other, right, that's the intersection, then only the parts that are doubly shaded satisfy the intersection, right? It has to be in both of those parts. And so if I put these on top of each other, can I do that to make it smaller? I'm cheating because we already know the answer. And then from that, magically, you see, it's beautiful that it's just this. Is where you have double overlap. Maybe I'll delete this or erase this. The orange. That's the idea. Obviously, there's fancier math that we could do, but I'm convinced. Are you? Oh, and then I think there's another one. Oh, and then we can do the same thing for the complement of the intersection is the union of the complements. Notice how they're not the same. All right. And the involution law. Never heard of it. That doesn't mean anything, but if it comes up, I'll talk about it. I don't know. Yeah, so the complement of the intersection is the union of the complements. Words. I know. Brutal. There are no questions in this section that we're going to cover. Just doing what Paul did. He said, empty set. Said, moving on. Great. Oh, back in chapter 1. Feels good. That was our little foray into 4.2, right? The laws. The Cartesian product, if you have two sets, then you can take the product of them. But what happens is when you take the product of two sets is it generates these ordered pairs where the first element is from the first set and the second element is from the second set. Okay, so it's any combination of first from A and second from B. Okay, and so A, I'll read it as times because the Cartesian product of A and B is kind of long. So A times B is the set of all possible whose first component comes from A and whose second component comes from B. And so if you have A is 1, 2, 3, and B is 4, 5, nothing crazy here, but even taking the Cartesian product of those tiny, tiny, tiny sets, right? You get quite a large set, right? First element from A, second element from B, until you've exhausted all the options. So 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, 3, 5, right? And that's just tiny. Okay. What that leads us to, though, is the cardinality of the Cartesian product. And so the cardinality here, cardinality is the number of elements in the set, right? And so the cardinality of the product is 6, which is the product of the individual cardinalities, 3 times 2. And that's going to be true always. And so that's kind of a nice thing. I guess the idea being, if you had to list all the products, at least you know how many you should have. I missed one. Where is it? Where is it? Just start over. Take it from me. Okay. And we can take the Cartesian product of a set times a set, that's totally fine. Just kind of boring, I guess. 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, right? That kind of thing. Oh, I guess I didn't need to highlight it up here. I have it in a box. It's doubly important. It extends to 3 or more sets. You just keep going and going and going. And remember, all you're finding is the cardinality. You're not finding the actual elements. It's just telling you how many elements it would have. Okay. Okay. A power set is the set of all possible subsets. Okay. So if you have a set A, the power set of A is the set of all subsets of A, and it's denoted by this fancy P of A, for the power set of A. Remember that the empty set as well as A itself can be subsets of A. They are subsets of A, right? And they're both included in that power set, okay? Which means that the power set of the empty set is a set with one element, which is the empty set. Wow, crazy. I know. Well, it just does. How about the power set of the set of 1? Well, then we remember that the empty set is a set. It's a power, it's a subset of any set. And 1 is just a subset of 1. So even if you do a subset of itself, it's just a set of 1. And so here you have the power set of 1 has 2 elements. What if you kick it up a notch, right? 1, 2, now you have 2 elements in your original set. Now the power set, you start off with the empty set. That's a good start. You could make a set of just 1, a set of just 2, or an improper subset of itself, 1, 2. All right. And those are all the possible subsets of this set 1, 2. Okay. And in chapter 2, we're going to talk about counting formulas that'll help us figure out how many we have given some number of elements in the original set. But parking lot that for now. Okay, power sets. Good. Oh, that's what I had a little mental note. There was an interesting problem in there, but I'm pretty sure there's an error in the answers, and sure enough, they'd taken it out in the version that I was working on, so I'm on to them. Don't worry, I'll send them an email. But here's more Sage Math. We'll kind of breeze through it for now, but these are the exercises we'll focus on Friday. Okay. Is this where? There's one I had beef with, but doesn't matter. Wow. They said it couldn't be done, but if you blab long enough, you can get through sets. All right. Last thing we're going to talk about is summation notation. Fun to say, fun to do. Extends to more than just sums, right? And that's how we're going to use them. But summation notation is just shorthand for things like a subscript 1 plus a subscript 2, 3, 4. That's called a series. And how we can summarize that, pun intended, I guess, because it's a summation, how we write it is with this capital sigma, and we have some value, what's it called? The index. Okay. So you start at k equals 1 and you move through to k equals 4. Now, these things are all written out kind of explicitly in this next box, so don't worry about that. But how we read this is the sum of AK, where k goes from 1 to 4. Okay. So let's see here. I'll put it over here. K equals 1 to 4 of a subscript k. Now the a doesn't change because a is another variable and it's not part of the index. So the only thing that's changing here in this summation is a1. So you start at k equals 1 and you move through to 4, right? And so this makes a plus 1 plus, or a1 plus a2 plus a3 all the way to a4. Right? Just a condensed way of writing it. And you guys are have you worked with things like this already in your programming careers?
Then we'd just be like, sorry.
Okay. I guess if you haven't done a race, but who knows? Who knows? We don't have to specify the endpoint. Sometimes we just want some generic endpoint n, right? So then k equals 1 to n. So here, k is the index, okay, the index of summation. And a subscript k is what we call the general term of the series. That's the thing that's going to be just morphing a tiny bit as we change the index, as the index moves through 1 through n. The initial index, the terminal index, right? I guess it wouldn't be until 4 loops for I in 1 to n, blah, blah, blah. Do this, do that. It is.
I've never thought about it.
There you have it. There you have it. Do this loop through, but just add them all up as you go. Okay. Those are sums. Now, the reason we bring those up, summation notation is super handy, especially if you want to save some writing, but it extends to other things as well. As long as you're applying the same operator, right? You can group them all together, right? Find the thing that's changing. In this case, it's the subscript of a, right? But then you just take the intersection over 1 through 4, right? And so then you can use this kind of notation of the intersection of a subscript I from I equals 1 to 4, right? And you just keep doing it until you run out of indices, I guess. Can even get crazy. Do the Cartesian product. Well, of course you can do the union. You can do the intersection, you can do the union. Cartesian product, go nuts, right? Just keep doing it. That would make a real mess, I think. But I don't want to do that. Symmetric difference. No thanks. Now take away the overlap. Now take away the overlap. Now take away the overlap. Okay. And these are just good for practice. And we're not doing anything really crazy with summations. Just 1, 2, and oh, you can also do the product. There's a wild card. Okay, we use a capital pi to denote the product, but this one's more common, I would say, than the symmetric difference one, for example, right? Summation and product notation, they're good to have. But the idea is the same, right? You just multiply these values instead of adding them. All right. So extension's not too bad. Wait, whoa. Oh. Crazy. We need more material. No, we don't. That's plenty. I fear I went too fast, maybe too slow. Just right. Not enough examples. Well, that was the plan. We had a plan. Anyways, it's early. I can give you time to work on those problems, but I'll stop the recording here. How about? Because it can get real boring. But yeah, so I'll stop that here.